Alright. The investigation is up under modules. There's three parts of it. There's a marking rubric, there's a format which will look very familiar to you because it is essentially the same as the Sydney Harbour Bridge. It's the same as the one you do in stage 2. And then there's the actual task sheet. So I'll make that, open that up. There are three parts of the task sheet. We're going to do A in its entirety today. I'm going to show you how to do B almost in its entirety. Most of your time on this task will be spent on C, where you'll all do different things. Alright, the task sheet looks as follows. You are to investigate how to make cake tins. Cake tins have an open top, so the cake can jump out. And you are going to use mathematics to make conjectures and then prove these conjectures. Conjectures in mathematics are a fancy word for a hypothesis, or an observation that you think will always happen. Part A. We're just going to jump straight in. This is a cake tin. It's a square one, and the way they make a square cake tin is they take a square piece of tin metal and they cut a little corner out of each edge. And we're going to start off with pretending that this length here is 5 centimeters. You're looking at a very baby cake tin. 5 centimeters by 5 centimeters. Now what that makes is a box. Pretend that's a square. And that box has come from a square cake tin with corners cut out of each of it. And the question is, how big should I make these cuts, which we're going to call x in length, how big should those cuts be to make the maximum volume of the box, or the cake tin? So the overall length of the sides is 5, and I'm going to cut a certain amount out. Now, before we even start, we can probably recognise that if we cut 0 out, we're not going to make much of a box. And if we cut more than 2.5 out, what will happen? Yeah, so 2.5 is kind of the biggest cut we can make, because if we cut 2.5 and cut 2.5, we've kind of cut it all out. So we are instinctively thinking that, well, x is somewhere above 0 and somewhere below 2.5. And we're feeling like if we are cutting out nothing or we're cutting out 2.5, the volume of our resultant box is not going to be very big. Yes?
Is this like we're cutting off the corners so you can fold up the side?
Yes.
Oh, okay.
So this length here becomes this one here.
Oh, yeah.
If that sort of makes sense when you're visualizing it. Like that edge folds up and makes it that one there. Alright, so from the 2D shape, let's think about how we will make the 3D shape in terms of dimensions. For the 3D shape, how high is our 3D shape? X, lovely. It is X high. If I cut X out and folding it up, it'll be X high. Given this whole length here is 5, after the cuts have been made, what is the length of the base? Beautiful, 5 take 2x. It is the length of 5, subtract off the x, subtract off the x. That length is 5 take 2x. And you're happy that the depth of the box is exactly the same because it's a square base. So it's 5 take 2x and 5 take 2x. Cool. Alright, so let's think about volume of a box. Volume of a box is length times width times height. Cool. We have these in x's. Our volume as a function of x, so v of x, is length, which is 5 take 2x, multiplied by width, which is 5 take 2x, multiplied by height, which is just x. And you guys happy where that came from? Alright. Now, we want to try and maximize this. We want to find the maximum volume. So we've done some practice questions on maximum volume, and this might feel vaguely familiar to one of the textbook, because it is. The maximum volume question is, we're going to expand, simplify, collect like terms, differentiate and find where the slope is 0, because that will give us max and mins. So the rest is a bit of an algebra slog, but I'm going to expand and simplify this out. So v of x is equal to 25 minus 10x minus 10x, something for x, plus 4x squared, and all of that is still in brackets with this electane on the end. Then I'm going to do a bunch of things in one step. I'm going to combine these two, because they're minus 20x together, and I'm going to throw x into everything, and I'm going to write it around the right way. We like seeing the highest power at the front, that's just how we do it by convention. So I'm going to combine, throw the x in, and put the highest powers towards the front. V of x is 4x cubed minus 20x squared plus 25x. So a few steps at once there. And you might have realised we've reached this bit. Sweet. Turn the heater off before we all cook or you guys go to sleep. Next step, we want to maximise this. So to maximise this, we find its derivative. V dash x is 12x squared, take 40x plus 25. Then to maximise, we set the derivative equal to 0 and solve this. So I'm just going to write a really ugly equals 0 on the other side. Now solving it. Solving it we can aim to factorise, but there is one way that will always work for us. Factorising can get nasty. The one way that always works is quadratic formula. Because we've fundamentally got a quadratic set it equal to 0. So we're reminding ourselves that that's A, that's B, that's C, and then we're going to use quadratic formula. So, x equals minus b plus or minus square root of b squared take 4ac over 2a. X equals b squared, minus b, minus 40 is positive 40, plus or minus the square root of b squared take 4ac. Now, b squared is minus 40 squared, take 4 lots of a, lots of c, over 2 lots of a. You guys forgive me using the decimals and the multipliers. I really hope the camera can see that. Alright, then we can grab our calculator, and our calculator will help us do a bit of this. Plus or minus square root of minus 40 squared is 1600. 4 times 25 is 100, times 12 is 1200, over 24. So clearly you're not having to rely on your head to do this, your calculator will help you out. X equals 40 plus or minus square root of 400 on 24. Anyone happen to know root 400 off the top of their head?
20.
Beautiful, 20. So this is 40 plus or minus 20 over 24. So x is equal to either 60 on 24 or 20 on 24. Now, we don't typically leave things written in the least simplified form, so we're going to simplify it down nicely. X is equal to, I can take a 12 out of both of them. If I take a 12 out of both, I get 5 on 2. I can take a 4 out of both. If I take a 4 out of both, I get 5 on 6. Cool. So we have two x values where the slope is 0. That's what we found so far. Two x values where the slope is 0. We need to know which of them is the maximum. We probably instinctively have an idea of which might be the max because one of them is 5 on 2, 2.5. And we decided way back here that if we cut out 2.5, our volume was going to be basically 0 because we've cut out 2.5 and 2.5, so nothing. So we're kind of feeling like this is probably not the max. This one is our leading candidate. But we have a way to show that something's a maximum minimum, and that is a sign diagram. So, a third step to this is a sign diagram for v dash x, and the things we're interested in is 5 on 6 and 5 on 2. And then we take values either side of this, And if we're being really strict about it, I should have an arrow here, because it doesn't go on for negative that way. I can't cut less than 0. I should stop here at 0. We've decided we can't really cut less than 0, that would be silly, so the arrow that way doesn't matter, or doesn't make sense. That's a good ending point here. Then we put in values either side, so we need to pick a value between 0 and 1/6, sorry, 5/6. A good value would be 1/6. We can take 1/6 and put it into the derivative. It'll be positive. We can put a value between 5/6 and 5/2, like the number 1, and put it into the derivative. It'll be negative. We can put a value between 5/2 and up. It'll be positive. What this gives us, and you don't have to draw this bit in, is up, down, down, up. This is the max. Our maximum solution is to cut 5/6 of a centimetre off the corner, and that will give us the best volume. Alright, so this is our solution for a 5 centimetre cake tin. 5 by 5. The question doesn't really ask just for 5 centimetre cake tins, it's really asking for all cake tins. So, what we're going to do is we're going to do a couple more, say this is an example for 5, we can do a couple more different cake tins and see if we can spot a pattern. Does that sort of make some sense? Alright, I would like you guys, what length cake tin would you like to do? Pick something that's not 5.
12.
12, cool. You guys are doing a 12 centimetre cake tin. You 4, what would you like?
10.
10, beautiful. What would you guys like? 9. Cool. Alright, so L and X. Now, I want us to build a table collectively. I have done 5 and decided that the best answer is 5/6. You guys are going to do 9, or is it 12, and 10. Cool. Go. You're starting with the same square, but a different number there that's not 5. You be quiet. Make them do it themselves. So, exactly the same process through, using quadratic formula, starting with 5. Starting with not 5, with a different number here. Hello. Beautiful. That's okay. No, this is the proof. They will all have that fact. Sure.
Just it's there.
Yeah, so I guess all, like, how would you express all the ratios now? Right now you've got L to 2L or L to 3L. How do you get all ratios?
It's this 6.
And there's quite a few ways you can do this.
No, it's not.
One way is it's like
I'm not doing 12.
Or
Yeah, actually.
or you could do R to S, which is the way to touch it. Yes, or you could do any pair of numbers. Because a ratio can be any number pair that doesn't have a common denominator.
So I could do like L to AL and see what it does.
You could do 1 and L.
Where'd you get it first?
Because you can effectively convert any ratio to a 1 to L ratio. You could do a lot of options, but yeah, so you have to prove for all ratios. Hello?
Is this just the same?
Yes. And hopefully that makes some sense with the logic. Instead of starting with sine length 5, starting with sine length 10,
Yeah.
so it's 10 take 2x, 10 take 2x
So
by
10
x.
is the whole length, yeah?
It was the whole length before the
Like
cut.
before it cuts?
Yes.
Oh, now it makes sense.
He's lost it. It will all make sense. Alright, and you guys are doing, was it 8? 12. 12 is good. 12 is a really intermediate answer for this thing. Let's see,
Square
work
root
out.
4.
It's only for me because I know what the answer is going to be.
Why do you want to do it? Square root 4.
They are, yeah. But it's nice in terms of numbers. So yeah, when you talk about limitations, you're going to be saying, really, you're going to want to take the edges off.
542 x minus 38x squared plus for it anyway.
It is, yeah. So we shouldn't have that plus on the right hand side. It should just end there, shouldn't it?
Yeah, but how you just extend it instead?
Yeah, you can. Yeah. So when you're writing it up, you can actually it's just wrong. And you can explain why you do it. It works. We like it working. It does have potential to do average soup, doesn't it?
This is still a quadrant.
Don't we have to rejumble this?
It's not a quadratic, but that's okay. It doesn't have to be
Oh, yeah.
because you're about to differentiate it.
Oh, yeah.
If that makes sense.
Oh, yes.
Yeah, that's not my point, is it?
Oh, okay, I was gonna say.
Wait, what is this? You know it. Your sleeves are 2 and 6. Well done. But you also know that 6 is right on the edge, which is good because that's what we found the first time.
Yeah.
So you're kind of expecting a 6 to appear there. That would be nice.
Because I heard someone distance above say.
Yes.
The center things in the rear one up the
Because when you write minus 72 squared, that is different.
Yeah.
Actually, that's different to the minus of 42 squared.
So you bracket them.
Yeah, the brackets are important.
Oh,
And also if he is 7, it's plus 7.
I didn't
Yeah, I
do
wrote it once.
Yeah, I put it into the four times two. Have I put that all in one? Maybe 12.
Oh, I see.
Yeah.
There you go.
And that should be too small.
I know, it's just fine.
Yeah.
I got 9.
You ready? Exactly.
Okay, there in a minute. That's exactly what it is. You think it's not what it is. Instead of starting
This
this
is to do with like, what's in the bottom of the
is that not right?
So we use
then you're going to have L 24. And you're right. It doesn't mean that that's it. Hello.
Is this right?
Yes.
Oh,
really kind of.
5/1.
That's right.
Yes, it is.
L
You should probably be suspicious, and then I'm like, well, not suspicious. You should be happy to see that. That would be cutting into the middle, which is what we saw here.
Into the.
And you know, that's definitely not 5. That's not the answer.
Oh, wait.
I got
That's
4.
5. 5 must be the minimum.
Yes. So your other one being 5 on 3 is correct.
You do? You try, I was like, it's your hand.
Let's make sign diagram.
Alright. Have we reached the point where we've got answers?
Yep.
Yes. The group doing 12, what did you guys get?
2.
2, yes. The group doing 10, what did you guys get?
5 on 3.
5 on 3, lovely.
We did not get two.
You did. Or did. What did you, group doing 9?
I got 9. 4.5.
4.5. 9 on 6.
Both.
Hello! Well done.
Is it not
Do you remember this?
understand?
K10? Mildly traumatic. Well done.
Yeah, 3.
Alright, now, we want to spot a pattern.
5.
9 on 6, 5 on 6. Life is going good so far. then 2 and 5 on 3 feel weird. But are you happy that I can write 2 as 12 on 6, because that's the same number. And if I wanted to, I could write 5 on 3 as 10 on 6. Can anyone spot a pattern with our best answers? Yes?
Divide by 6.
It's whatever the length is divided by 6. Alright, so if we know the length of the cake tin plate, or the base, was 5, 9, 12 or 10, our answers are 5 on 6, 9 on 6, 12 on 6, 10 on 6. If I gave you a length that's unknown, a length of L, what do you think should go there?
L on 6.
Yes, L on 6. Cool. That's what we call a conjecture. We've basically guessed that that looks like it should be L on 6. For any length base, I should cut 1/6 of the length out, 1/6 of the length out, and that will get me a box of maximum volume. Now, last step is prove the conjecture. We need to prove that is true. So, let's do that. Do you guys want to have a go, or do you want me to just do it? Oh, we're going to start, instead of a box length 5 or 9 or 12, let's start with a box with base length L. And I'm just going to clear some space. Alright, if we've started with L, and we're cutting X off the corners, and we go back to our volume equation and think, well, length times width times height, and now volume is a function of X, what would our new length be?
L minus 2X.
L minus 2x. Nice. Exactly like the two previous examples you guys have done, it would be this total length, take off 2x. The length is going to be L, take 2x. What would the width be going the other way? Same. Yeah, it's a square. So L take 2x. And what's the height of this box? X. Nice. Well done. Alright. This feels vaguely familiar. You've seen it done with a 5 in front, and you've done it with a 12 there, or a 9 there, or a 10 there. We're just going to roll through, but with the L. So L's just a constant in this case. We're going to expand, simplify, differentiate, carrying L the whole way. Does that make sense? Cool. Alright, go. You guys expand and simplify. I'm going to ask Harry's question, and then I'm going to come do it on the board as well. Hello. They're not right. Oh.
Technically it's like that. Because it's 2a Lx squared. And that's just 2.
Yeah, they're not right. Oh.
They're not like the same Lx squared.
They're German squared.
So 4a.
I would say do a partial factorization.
But what?
So factor out x squared, and then you've got like bracket. Oh no, not from everything. Just the middle. That's just the two terms we're talking about. The reason you want to do that is so then you get the coefficient of x squared. Oh.
So are you saying x squared is here? I've got 4x squared. Is that right?
I'm going to do it here.
We like cross out here, so.
Sorry. Alright, expand this out. L times L is L squared. Take 2Lx. Take 2Lx plus 4x squared, and we still have the x at the front. Then I'm going to do the same combination of things I did before, multiply the x in, combine like terms, sort things around so they're in the order that I like. 4x cubed minus 4lx squared plus L squared x. So it's important to note that I can take 2lx and take 2lx, and let's take 4lx. Fairly happy that we got there? Cool. Now we're going to differentiate. So we're looking for v dash x. We are going to remember that L is just a number here. It doesn't play a role in the differentiation other than treat it like 4. What lots of students would do here is they see an L squared and they feel the urge to drop that 2 down the front. But you're not going to. That squared isn't above the x. You're not differentiating in respect to L, you're differentiating in respect to x. So you're doing the rule on the x's, not on the constants. So this becomes 12x squared, take 8lx plus L squared. So L squared x just differentiates to L squared. Then we set that equal to 0, and now we go quadratic formula, which is where it's the most fun. So then x equals, and you have to be pretty confident that you know that, well, your A is 12, your B is minus 8L, and your C is L squared. So just before you go into quadratic formula, remind yourself of what your coefficients are, and it's okay that your coefficient has an L in it, because frankly you want an answer with an L in it. Alright, B squared, take 4AC. B squared is minus 8L, oh sorry, it's minus B, so don't square it yet, minus B plus or minus the square root of, now we do B squared, take 4 lots of A, lots of C, over 2A. And this is where being able to work with surds and things is really useful, because our calculator is only so helpful here. Because we can't hack the calculator can't hack the L. Minus minus is plus, so this is positive 8L. Plus or minus square root of minus 8L squared is positive 64L squared. Take 48L squared over 24. Now, conveniently, these guys are alike. They both have an L squared, so let's simplify in there. X equals 8L plus or minus the square root of 16L squared on 24. 64 take 48, 16. And we're feeling like things are kind of nice now. 16 is such a nice number to have there. This root can be applied to both things inside. Now we've got rid of the plus or minuses in there. So what is the square root of 16L squared? 4L. Beautiful. So this becomes x equals 8L plus or minus 4L on 24. Let's split that separately. 8L plus 4L means x is 12L on 24. Or 8L take 4L is 4L on 24. Now, let's simplify. Highest common factor out of 12L and 24L is 12. If I divide the 12 out, I get L on 2, which we were definitely expecting as the minimum. And we take the 4 out, L on 6, there we go. Yes?
How do we prove it's L and 6 if you can't do a sign diagram?
You can. And that's the nasty thing. And this is where you'll need to do it in your write-up, but it's a great question. L on 6, and I'm saying the minimum here is 0. L on 2. And really, we can't go beyond L on 2, so you might want to just leave it there. But we want to prove that that's a maximum. Yes,
Are we supposed to put a sign diagram into Word?
with great difficulty. And frustration and pain and tears. Word will let you draw arrows. There are tools online where you can go to sign diagram maker and it'll make you a sign diagram. Frankly, if you ask AI to draw you a sign diagram, I am okay with that AI use. But in the past, this is how you will have done it. You will have done, excuse the random Word document I'm trying to touch up here, you will have done draw, you will have either tried into shape, or you will have gone insert. Somewhere in here you'll find an arrow. Shape. That. And then insert shape line. And then insert text box. Simple text box here. And make it small, and then you're like L on 2. And then you're going to type something, and every single one of those components will go to different places in the Word doc, and you're going to cry and curse the world and wonder why you can get a pizza in 10 minutes but you can't put an image in there. It's a problem really more for you guys, but yeah, you'll have to draw a sign diagram in your write-up. If you want to handwrite it and insert an image in of your handwritten version, I'm okay with that as well. I'll admit it is a frustrating proposition, but yeah, you'll need to do a sign diagram. The bigger question here is how you actually enter a value in. Can you guys pick a value between L on 6 and 0 for any value of L?
L on 8.
Good. L on 8 would work in fine. L on 8 must fall in there. Same with L on 12, L on 10, not fussed. L on 8 is a completely legitimate thing for you to substitute in here. If you substitute into the derivative, and remember you're substituting it in to x and x squared, then you're going to get a whole bunch of L's, which isn't bad. You know that L is a positive number, because you have to have a positive length. You should be able to convince me that subbing L on 8 into here gets you a positive number. Similarly, what's the number between L on 6 and L on 2?
4.
Yes, L on 4 would work beautifully. If you take L on 4 and sub it into there, you should be able to convince me that that's always going to be a negative number, and therefore that this is a maximum. Yes?
How do you draw L on 4?
Well, when you substitute it into here, where x is, there, and there, and there, it should come out with something that will always be negative. Try it. I'm not going to show you guys that one. You guys can have a go at that yourself. But yeah, you should be able to convince yourself it's negative. Alright, we've done part A. Part A, we've proven the best result is L on 6. Cool. Admittedly, there's a lot of work to do. You have to type it up, you have to explain it, you have to do the substitution, and then talk a bit more about cake tins. But other than that, we're pretty sweet. Do you want me to show you part B? Cool, let's do part B. I will let you have a little read of part B, find a new page while I clean the board. Oh, sorry.
It is always good to code.
Mr. Dimbo,
Yes.
how do you find that the plus and minus is here?
You substitute it into the derivative. And if the derivative is positive, it's a plus. If it's a negative, it's a minus. Mr. Harry.
So I tried to take out x squared, and I got take 2x squared brackets, and I take 1 of those brackets.
What you should have is something in front of an x squared. Then you've got the coefficient of x squared.
That is not what I have.
Okay.
Yeah, of course.
Not today.
Is that-
No more.
I mean, you can cut it out. You're in a minute.
Alright, part B of this. Having enough time, we're good. Part B of this is no longer looking at square cake tins. This time we're mixing things up and looking at rectangular cake tins. There are lots of different types of rectangles. I'm going to show you one example for a 2-to-1 rectangle. And by 2-to-1, I mean one side is twice as long as the other. So a 2-to-1 rectangle, if I let this side be, say, 3, what would the other one be? 6, cool. 5 there, 10 down here. A 2-to-1 rectangle, one length is twice as long as the other. I'm going to run this process through with 2-to-1, and this is the slightly mean thing. I'm expecting you guys to pick a different ratio for this. So I'll do it with 2-to-1, and by all means take the notes with 2-to-1, but I don't want all your write-ups to have a 2-to-1. You can go 3-to-1, you can go 2-to-3, you can go 5-to-4. So a 5-to-4 one sounds weird, but if this is 5, that's 4. If this is 10, that's 8. If this is 20, that's 16. So you can imagine a different family of ratios. Yes?
So you don't write up the 2-to-1.
No, don't write the 2-to-1.
Can we write it as a different length?
But you've
now?
done other ones, huh?
Can we write it as a different length while you're going through it, like now?
If you're confident, yeah. Eventually where this is going is, I'm going to show you how this works with a 2-to-1, where I might let this be 3 and this be 6. I'm then going to show you with all 2-to-1s. And then you guys are going to prove your own family. 3-to-1, 2-to-3, etc. That's a family of ratios. Some of you will go the extra step, going further. Can you find the length for all ratio pairs? So for all families. But I won't, not everyone will do that, which is fine. Alright, so a 2-to-1 ratio might look like this. Same thing, we cut out a square from each corner, which is x. And we fold it up. Our run through is going to be very, very familiar. Volume is length times width times height. Volume is, in terms of a function of x, what is the length of my tin?
6.
Sweet, take 2x. 6 take 2x. What is the width of my tin?
3.
Cool, 3 take 2x. So it feels familiar, but it's no longer a square, and the height is x. Now, expand, simplify, collect like terms, then differentiate. We're running the same process. So if you're doing it on your own ratio, go for it. If you're doing it on mine, you can copy this exactly. 18, take 12x, take 6x, plus 4x squared. Throw in, oh, not the power of x, throw in that x, becomes 4x cubed, take 18x squared plus 18x. V dash x, differentiate, becomes 12x cubed, take 36x plus 18.
12x squared. 1.
Yes. Is it not?
12
It's 12,
cubed.
yeah.
Squared. It's alright, thank you.
What's else?
Yes. That's fine.
Thank you.
Good catch. Alright. Then, to make the numbers a little easier, I'm going to factor out a 6, just for my own sanity, to keep the numbers small. 2x squared, take 6x plus 3. And it's equal to 0. Now, our solution will come from the quadratic equaling 0, so I'm really interested in what happens when we solve this quadratic. A, B, C. And I'll give you a warning, there's no way this is going to be as nice as the first one through. So, x equals minus b, plus or minus the square root of b squared, take 4ac over 2a. So, same set of substitutions. X equals 6 plus or minus the square root of 36, take 24 over 4. X equals 6 plus or minus root 12 over 4. X equals, now it's probably worth going up to the side and recognising how we can simplify root 12. Root 12 is the same as root 4 times 3 is the same as 2 root 3. So you're going to have to play a bit around with square roots, but root 12 simplifies to 2 root 3. So this becomes 6 plus 2 root 3 on 4, and 6 take 2 root 3 on 4. X equals, and you cancel a 2 out of everything, 3 plus root 3 on 2, and 3 take root 3 on 2. It's not as nice as the first half, but that is okay. Those are our solutions. Once again, we're suspecting one of them is a positive, or one of them is a maximum, one of them is a minimum. This is 3 take root 3 on 2. This is 3 plus root 3 on 2. Don't know why I've written above the axis, not below. Sorry, normally you write it below. And then we're going to substitute in values. A good value to pick here. What number is between 3 take root 3 on 2 and 3 plus root 3 on 2? What about just 3 on 2? Because this is 3 on 2 take something, and this is 3 on 2 plus something. 3 on 2 is in the middle of that, if that makes sense. This is a minus, isn't it? Negative in the middle. That is our maximum solution. 3 take root 3 on 2. What time is lesson end? 11, isn't it? Cool, that's some time. Okay. That's my solution to the maximum. Yes?
So there's arrows on both ends for this one?
Well, I can't cut off less than 0. And then here, I wouldn't arrow it either. If I'm cutting off, what's the maximum number I can cut off?
6.
1.5.
Yeah, 1.5. Because if it's 1.5 this way and 1.5 that way, then this cut will go all the way into the middle, which will make no shape. So the maximum is 1.5. Weirdly enough, I don't think this is even possible. I don't think you can cut 3 plus root 3 on 2 off the shape. That number is too big to try and cut off. So actually, this isn't even a possible solution. So when you draw the sign diagram, really, it's going to end about here, at the 3 on 2. And this is a solution thrown up by the quadratic formula, but it's not a solution that we could ever actually cut off the shape. So, if I've got red, this is definitely not a solution. Our answer is that one there.
So if you're drawing that on the report, how would you do the sign diagram?
I would show the full sign diagram, because that's the mathematical answer. And then underneath, you'd say, in reality, this isn't possible. It's not a possible solution. The only possible solution is this one here. This one would be a minimum anyway, but it's an impossible solution. Sometimes formulas throw out what look like number solutions, but they're not possible. So then the standard practice for SACE is to show the not possible solutions, to show that you found all of them, and then make a decision and show that you've made a decision to discount them. Martin?
You just write the domain.
Yeah, you could also start the problem with the domain. So right here, before you even start, you could be limiting x as greater than or equal to 0, less than or equal to 3 on 2. And then you can make the argument that when you find it here, that actually that's out of domain, so therefore it isn't a solution.
I was going to say, what makes it not possible?
Because, imagine if you're cutting a corner off here. If I made a cut that's 1.5 and another cut that's 1.5, I'll cut all the way into the middle, and I'm not getting much of that. It won't box properly. It won't do anything. All right, I've shown the solution for a particular rectangle, a 3 to 6 rectangle. Let's say I want to repeat this, but instead of a 3 to 6 rectangle, I want to show it for all families of 2 to 1. The way it would work is, I'm going to let this side be L. What would this side be? Good, 2L. L and 2L. Alright, I'm going to restart mine here. If that's L and 2L, my new volume in terms of x, Vx, would be 2L take x, L take x, multiplied by x. So I guess we're happy that we're running the same thing through, but instead of 6 take 2x, 3 take 2x, it's now 2L take x and L take x with an x. This will give me an answer for all 2 to 1 rectangles in terms of L. Then, same process. Expand, simplify, collect like terms, tidy it up. 2L squared, take 2LX, take LX plus. Guys, you've got to yell at me when I do wrong things. Someone could have earned a Mentos there. We're not taking 1x, we've never taken 1x. We're taking 2x's. 2x. 2x. Cool, let's go again. 2L squared, take 4LX, take 2LX plus 4x squared x. And what you should notice when going through this is that each line should pair up with the line that you did with a real number. For example, 2L squared. Remember when I did it with real numbers? My L was 3. So where I say 2L squared here, on my original one it should be 2 times 3 squared, which is how that 18 appeared. And then the next one here, 4LX take 2LX, is going to line up with this bit and this bit. So my original one, L was 3, and we can see it working out with numbers. Now we're just carrying the L through. Alright, so this becomes 4x cubed take 6LX squared plus 2L squared x. Oh, I remember the space here. Let's differentiate. V dash x is equal to 12x squared take 12LX plus 2L squared. Yeah. Then set that to 0 and then think about what our A, B and C are. A is 12, B is minus 12L, C is 2L squared. And we can sort of double check that these lined up with our equivalent statement up here. Minus 36 is the same as minus 12L, because here I made my L 3. If I put 3 in there, I'm sort of confident I'm on the right track. It's quite often one SACE methods, we do things with a real number first. We do things with like 3 and 6 or 2 and 5, because running it through with numbers is nicer, and then we run it through with a letter. Alright. X equals minus B, so 12L plus or minus, do you want me to do it bigger on the bigger board? If you're in the video, I'm really sorry. Square root, B squared minus 12L squared, take 4 lots of A, lots of C, over 2 lots of A. I'm going to go across to here now. X equals 12L plus or minus the square root of 144L squared, take 4 times 12 is 48, times 2 is 96. Take 96L squared over 24. tidying up. X equals 12L plus or minus square root of, what is 144 take 96?
Yeah.
Pardon? 48? Lovely. 48L squared. 48L squared over 24. Now we're going to do a bit of thinking about how we deal with root 48L squared. So I'm just going to do that over here. Root 48L squared. Now, the root can hit the L squared really nicely. That's just going to give us an L. What does root 48 give us? 4 root 3. You're happy that 16 goes in there 3 times. So root 48 is the same as root 16 times 3 is the same as 4 root 3. So this bit here becomes 4 root 3L. So our solutions are x equals 12L plus 4 root 3L. And traditionally we would write that as 4L root 3. It's not a good idea to leave stuff hanging off the end of the 3 here because it looks like it might sneak under the root. Over 24. And our second solution is 12L take 4L root 3 over 24. Alright, ugly, but we're now going to cancel out everything we can. So you can see there's a common factor of 4 in everything. I'm going to save myself a little writing and make that go to 6, that go to 3, and this go entirely. So our solutions are x equals 3L plus L root 3 on 6, comma, 3L take L root 3 on 6. And if we compare that to our answers here, say take this answer here, imagine I wrote that on 6, meaning I have to multiply top and bottom by 3. That is the same as, times that by 3 is 9, take 3 root 3 on 6. And remember that my L, before we started this, was 3. Because that was the L being 3 there. Here, 3L is the first part of the answer, tick, take L root 3, take L root 3 over 6. So it's in the same form, we've kind of confirmed that our answer here fit this pattern. Our solution is that one there. Meaning for every 2-to-1 ratio, you can cut out that amount in terms of L to maximise the volume. Now, that is now 2/3 of the task. Weirdly enough, on the SACE website, that is the entire task most people finish there. But that is rather dull. I've done the 2-to-1. You guys at some point at your own leisure will go away and do a different ratio. Then if you're feeling really fancy, try and prove all ratios. So for example, mine was L to 2L. Yours might be 3L to 4L if you're doing a 3-to-4 ratio. If you're going to prove all ratios, you have a bit of thinking to do. It might be L to AL. You might do R to S, which is what the task sheet kind of suggests. You might do 1 to L, because any ratio can be reduced to 1 to L if you divide both sides by a certain amount. So how you prove all ratios, up to you. Your answers are going to be vaguely messy, but they all come out something like that, and you can always verify them by doing an actual number version. I'd like to talk you through part 3. Hello?
So, for example, if we did like ratio of 1 to 3, we could just do it 3 to L. Sorry, 3L to L.
Yes. Yeah, so if you were going to do a 1 to 3, I would pick a specific example to start with. So a 1 to 3, you might go with like a 15 and a 5. Because that's an example of a 1 to 3. So you do it with 15 and 5, and then you do it with L to 3L.
Yeah.
And hopefully I've given you enough to work off that you can pull that off. Cool. Yes?
So doing it with all ratios, you're just pretty much it's all letters. Like, okay.
Yeah. Yeah. Alright. That's part A and B. Part C is where it gets a little more interesting. I think, anyway. Zoom. Part C asks you to consider a different shape you could feasibly use as a cake tin. So we've had students in the past do cylindrical, do hexagonal base, do a triangular base, do a what's it called? A circle but tapering in, like a truncated cone, meaning like a cone but with the top cut off. Like, there's a lot of shapes you could conceivably make a cake tin, and strictly speaking, we don't actually care if you don't go with a cake tin, so if you'd rather any type of container for storage, you want to find an optimal solution for your given container. Now, this often works when you have some constraints. The constraint we used for part A and B was a 6x3 or a 5 and then how much you cut off. Your constraints can sort of, set yourself up with a thing to optimize. For example, you might have a 1 meter sheet of metal and find what is the best cylindrical thing you can make out of it in terms of optimal volume. And then you set yourself up with a little problem where you've got a 1 meter square and you've got to like cut a circle out and then cut the rectangle out that wraps around the circle to make a cake tin. You could decide that you want to have 1,000 square centimeters and you're going to use that to make a triangular based pyramid. No, not pyramid, prism. How should you arrange the 1,000 so that that surface area optimizes the volume? Talk to me about your idea, because some people will think, what's the biggest cake tin I can make in this shape? And then their math tells them to make it 100 meters in every direction, because that's the biggest cake tin. You need to have something to constrain it. The something might be a limited surface area, the something might be a limited sheet that you're starting with. So talk to me about, is this going to work? Because it'll either work or it'll either fail because you don't have a good constraint, like it's nothing keeping it in place, or conceivably it might fail because you're going to need calculus you haven't learned yet, which is fine. And I'll just tell you, no, that's not a good idea, or try something different, or think about something else. You're also welcome to dive in deeper, and this is where you'll be diving deeper and thinking more consistently about it. For example, I'm not sure if you've ever baked a cake, but the cake tins don't really work like this. There's not a perfect round, like a perfect right angle on the edge, because your cake gets stuck in that bit. Instead, cake tins often look like this on the bottom. Like they have a slight curve, which you could model as, well, it's not quite a rectangle. In here, actually, there is a quarter circle to corner it off. In which case, how does that change the volume if you corner your corners? How does it change the volume if the metal expands and shrinks? There is a lot of places you can go with this. A and B are just sort of a starting point. Yes?
So you could do like a circle base one instead.
Yes.
But then you'd find like the radius and all that for it?
Good, yeah, radius and height. So yeah, in this here, your volume was length, width, height. For circle, it's based on radius and height, those two dimensions. For a hexagonal prism, it'll be based on the side length and the height. So depending on what shape, you'll have to play around with formulas. You're completely allowed to research formulas for different things. But yeah, and basically by the end of the term, I'd love you to have your part A and B down packed, which shouldn't be too hard given we've done all of part A together and part B we had a bit of a run through at. And then an idea for part C and making progress on it. And if we do that this term, then next term will be pretty smooth in terms of actually getting this done.
So part A is completely just have to do like the write-up for it?
Yeah. Part B, I've done it for 2 to 1. You guys have to do different. But it's not too bad. And part C, I haven't done it all. Yes, it is. Yeah, Harry's trying to prove for all ratios. It is kind of hard, but that's fine.